Okay, this is the third districting video. So we're going to continue with this cut edge model, but now we're going to impose contiguity. So for the contiguity constraints, if you can look at that PDF file that had all of the models in it, and the constraints that we're going to use are written out here. And the idea of these constraints is based off of flows. So what the model tries to do is it's going to identify a root or a source node for each one of these districts. So we've got 5 districts that we're trying to build, so we need to pick 5 different roots. In fact, more specifically, we need to pick 1 root from each district. Then once the model has chosen those 5 roots, then it needs to send flow from those roots to the other nodes of its district across the edges of our graph. So maybe if I think about it in terms of these instances. So let's suppose we've got our 4 districts here. This first column might be District 1, this is District 2, District 3, and District 4. So maybe 1 is the root of District 1, 2 is the root of District 2, and so on. So after we've identified those 4 district roots, then we're going to send flow across the district's edges. All of the flow will originate at our district root, and it will send, I believe we'll send 3 units of flow out of our root for these 3 other nodes in our district. So we'll send 3 units along this edge. Node 5 will consume 1 of those units. We'll then send another 2 units out of 5. Node 9 will consume 1 of those 2 units. And then the remaining unit of flow will go across this edge to node 13. So what we do is we essentially generate flow at each one of these roots, and we send it across the edges of our districts. And one key constraint here is that we do not permit the flow to cross these edges that are cut. So that way that the flows are only going kind of internal to a district. Okay, so that's the idea behind the formulation. The way that we write it out mathematically is a little more complicated, but first we start off with our root variables. So Rij is a variable that tells us yes or no, is vertex I or county I designated as the root of district J. So this constraint right here tells us that for each one of these districts J, we need to pick precisely 1 node I to be its root. The next constraints say that if node I is the root of district J, then that node I needs to be assigned to or part of district J as well. So you can't have a node be a root of a district and then that node be actually assigned to a different district. These F variables are representing the flows across the edges. So Fij is kind of the flow across arc Ij, and Fji is the flow across arc Ji. And then I mentioned that we don't permit flow to cross any edge that's cut. And recall that Ye is representing whether or not an edge is cut. So if it is cut, the edge connecting nodes I and J is cut. This Y will take a value of 1. So this will be 1 minus 1, so that'll be 0. So this right-hand side becomes 0, and then it forces both of these flow variables across that arc, either in the Ij direction or in the Ji direction, forces both of them to be 0. So this constraint tells us don't send flow across cut edges. And then essentially these other constraints right here are essentially requiring each of these nodes to consume a unit of flow. essentially. So, oh, and maybe I should specify before I get to that. There's this parameter m right here. So this is like a constant, which I think in our case you could set to be something like the number of nodes, or something slightly smaller than that, like number of nodes minus number of districts plus 1. But we could just say number of nodes. So that's essentially a bound on how much flow you would ever conceivably send across one of these edges. So if you consider any particular district, like in this case when we had 16 nodes split up into 4 districts, you know, the most number of nodes that you would ever have in a single district is actually 4. And so the most flow that you would ever send across any of these edges would be, you know, 1, or it'd be 1 less than that, because you don't need to send any flow to the root. It already exists at the root. So the most flow in that solution that we had talked about that you'd ever send across a single edge was 3. But if we use something like 16, that would also suffice. Okay. So that's, this m is kind of a large enough value so that when an edge is not cut, so when this y is 0, then this right-hand side becomes this capital M. And when it becomes this capital M, it permits just about anything. We could send as much flow as we would want ever, that we would really want to do in a feasible solution. Okay, so that same M is actually used in this constraint as well. And what this constraint says is, suppose you're looking at a node I, and this node is not a root at any district, so it's some non-root. In that case, it needs to consume a unit of flow from one of the roots. So in this constraint, it says if it's not a root, then all of these R variables equal 0. And so then this right-hand side of this constraint becomes 1 minus 0, or just 1. So this right-hand side becomes 1 when node I is not a root. And then on the left-hand side, we have, we're summing essentially the net flow across this node. So we look at all of the neighbors of I, which we're kind of indexing them as U. So U is a neighbor of node I. And we look at how much flow goes from U to I, and then subtract from that how much flow goes from I to U. So on net, in our columns plan, if you looked at node 5, we would have 3 units incoming and 2 units outgoing. So that difference of 1 unit is what node 5 is consuming, and that's what that this right-hand side is imposing. Okay, so that's kind of the idea behind these constraints. Let's go ahead and start implementing those. Okay, so what we're going to need to do is we'll go back to our starters, and we're going to do D4. Okay, so I need to edit this slightly. So one thing we need to change is the file path. So I'll just copy that from our previous one. Okay. We import cherry chain and read our graph. That all seems to work. Another change that we'll need to make is that with the 2020 data, we can't keep all counties whole with a 1% deviation. So I'm going to change this to 2%, but in your project, you should keep this as 1%. And then we have the total population and the lower and upper permissible district populations. It's written slightly different to how we did it in the previous video, but ultimately it's capturing the same exact idea. Adding spaces here just makes it a little easier to read. Okay, so let's run that with our 2% deviation. Okay, it doesn't like tot_pop because we haven't iterated over the nodes and done this sort of a thing. Let's copy that. I guess I'll need to do that. Maybe I'll add a cell here. Okay, so I'll iterate over the nodes. I will get the population that's stored in that field, and I'll assign it to that other field. How it works. And these should be the same L and U values that we had in the previous video. Okay. This should be pretty similar to what we did last time. Okay, X's are the assignment variables, Y are the cut edge variables. I can run that. Our objective is to minimize the sum of the Y variables, the cut edge variables, which I could do like this. All right, we have our assignment constraints, we have our population balance constraints, then we had our cut edge constraints. I think last time what we had done is wrote this a little bit. So let me make that match. If you wanted to, you could keep it as is, I believe, but I want to make it look consistent. That should be good. So I'll run that. Oh, I didn't run the objective. Okay. So I could, maybe it wouldn't be a bad idea if I tried to solve this right now. Just to make sure I haven't done something wrong. And it should give 37 cut edges, so just like we had before. So while that's running, maybe I'll start coding up the contiguity constraints. Okay, so first we need to add our root variables, so I'll call those R. We add this R variable for every node and for every district J, and these are binary. Okay, and then we need our flow variables. So we defined a flow variable for each one of the edges and in both directions. So if you recall here, we had for every one of these undirected edges ij, we would define a variable fij and a variable fji. So these are kind of the directed counterparts of this undirected edge. So to do that, it's okay. This worked out, gave us 37 like before, so everything seems to be going good. Okay, so in order to add these flow variables for each direction, you know, ij and to j as well as j to I, it's convenient to just go ahead and define a directed version of our graph. So I'll get that directed version of G by using this network X function. This is digraph or directed graph of G. And I don't know if I've imported network X. I might not have. Okay, I haven't imported network X, so I'll need to import that. So again, this is the kind of the directed version of our graph G. So now I can add these flow variables for every one of the edges in DG. So we get flow variables in each direction. Okay. I think that should work for the variable definitions. Let's check. Okay. All right, so now we'll add those constraints. So first we had something called capital M in that model, which was the number of nodes in our graph minus the number of districts plus 1. And this is based off of the idea that every district is going to have a root. So we have, k roots, and then the number of other nodes in the graph would be, n minus k. And so the most flow that you would ever send out of one of these roots is going to be something like n minus k. Okay. I think we might actually be able to take off that plus 1, but I'll leave it there. Okay. So one constraint was that each of the districts should have, each district should have one root. So add constraints. We'll add a constraint for all j in range k, constraint for every district. So, okay. So something is going to equal 1. And that something is, you add up all of those root variables over all choices of I. Okay. So we've now defined the f variables and the root variables. We've also defined these assignment type constraints for the roots. We pick one root for each district. Next, let's do these kind of coupling constraints that link the root decisions and the assignment decisions. Okay. So we want to add constraints for every I and for every j. And that constraint says Rij is at most Xij. Easy enough. Okay. So we have these latter two constraints left. So this, I don't know which one we want to do first. We'll just do them in order. So we'll do this complicated one first. Okay, so you'll see here we have a constraint for every node I. Maybe I can start typing that out. Okay. That constraint, it was a greater than or equal to constraint. And the right-hand side is 1 minus m times the sum of the roots. So 1 minus m times the sum of the roots. Rij for j in range k. So remember, this sum will be 1 if node I is a root of one of those districts j. Okay, so we've got the right-hand side of this constraint down, I believe. So now we need to add the left side. And the left side looks at all of the flows that are incoming and subtracts all of the flows that are outgoing. So we'll want to say, summing a whole bunch of things, it's going to be, let's see, fji minus fj. So that's the flow into I from j, and the flow out of I to j. And we should add this up over all of the nodes j that neighbor I. So let's say for all j in g dot neighbors of I. So this is something that's built into the network X type graphs. It has something called neighbors, and you just pass the node that you're interested in, and this will essentially return the set of neighbors. So this is something that I think we did in the Network X videos. Okay, I think I've got that one down. All right, so our last set of constraints say don't send flow across cut edges. So that's this constraint. So for every undirected edge, ij, we look at the flows in either direction. So let me start writing that. For every ij and g dot edges, these are undirected edges, and we look at the flow, let's say from I to j, and the flow from j to I, and this should be at most something. I think that thing was m times 1 minus double check that. Yes. Okay. I think that should be good. Let's try that. Let's see if it works. Okay, cool. Seems to have worked. So let's go ahead and try to solve. And this is another kind of difficult model. This may take a little while to solve. So we know without contiguity constraints, our objective was 37. So when we add extra restrictions, when we add these contiguity constraints, we know that our objective can only get worse. So since we've already apparently found a solution that cuts 40 edges, we're actually, I mean, Groby doesn't know it yet, but we know that we're actually pretty close. So optimal is going to be somewhere between 37 and 40. Now it's taking a little bit more time to improve this lower bound. And I think part of the reason here is because we have a larger model. So we have more variables, we have more constraints, and it's more difficult for Gurobi to solve the LP relaxation in each one of these branch and bound nodes. So it's not visiting them as quickly as it was before. So this will definitely take a little bit longer. I guess it still remains to be seen how long this will take. I'll go ahead and just sit here and wait and see what happens. I think I'll continue recording. Feel free to skip ahead until it finishes solving. It might take maybe 10 minutes, I'm not sure. Okay, and we're back. So took a little while, but ultimately 39 cut edges seem to be optimal when we impose contiguity. It took us about 1,000 seconds. So what does that come out to? About 15 minutes? So a little longer than I would have liked to have waited, but it's a hard problem. I understand. Give my computer a break. Okay, so maybe we go ahead and print district information. It doesn't like something. Let's see. Okay, so this is the old code from the 2010 census. So I need to change that to name 20. Try that. Maybe I'll add some spaces here. Okay, so the populations seem fine. Oklahoma County is by itself. Tulsa County, Creek County, and Osage County are all in the same district. So that seems like that might actually be contiguous now. And it should be, assuming we coded everything correctly and the model is correct. Okay, so let's proceed. We'll try to draw this. So I'll need to make sure I get the right file path here. For my shape file, go ahead and read the shape file. And let's use this code for drawing the districts. Okay, give that a go. Okay. So now we've got our 5 contiguous districts, and they satisfy our population balance constraints with a 2% deviation. And the shapes aren't all that bad. Okay, so that does it for the mid-cut lecture with contiguity. If you're interested to stick around, you can keep watching. I think I might have an idea for how to solve this more quickly. So the one issue with this model, as stated, is that there's this symmetry between the district numbers. You know, we could choose to call this green district District 1 or District 2, District 3, 4, 5. And likewise for the yellow district, as long as we chose a different number than the one we used for the green number, that could also be kind of a valid numbering for these districting plans. And so if once you've kind of figured out how to partition the counties across these 5 districts, you can number the districts in 5 factorial different ways. And this kind of introduces extra representations of a districting plan in our math model. And this is kind of known to cause troubles for branch and bound algorithms. So what we can do if we want to try to avoid this is that one thing we can do is just try to specify some roots for some of the districts. So we know, for example, that Oklahoma County is going to have to be in some district. So why don't we just call whatever district that is the first district? And then likewise, Tulsa County is going to have to be in one of these districts. And because of its population, it can't be in the same district as Oklahoma County. It has to be in a separate district. So why don't we just say that Tulsa County is going to be the root of the second district? I think likewise, let's say Comanche County, where Lawton is, I think it also would have to be in a separate district. Maybe we can look at the populations just to confirm that. So let's see. So Tulsa County has a population of around 670,000, which so definitely could not be in the same district as Oklahoma County. And then let's look at Comanche County. Oh, okay, so it's actually in the same one as Tulsa when we don't require contiguity. But I think if we require contiguity, I think they will probably have to be in separate districts. So let's give that a go. Let's try that. So I'm going to go up here. And after I define these root variables, I'm going to require that Oklahoma County is the root of District 0 in this case. And so I need to know what's the node number for Oklahoma County. So for that, I can look here. Okay, so node 6 is Oklahoma County. And then I can do a similar thing for Tulsa County. Make it the district, I'll maybe make it the root for District 1. Oops. Okay, so which one is Tulsa? That's node 34. Okay, and then maybe I could try to do the same thing for Comanche County. I'm not exactly sure if that would be safe to do. So we have about 800,000 people that we can put into a district, and Tulsa County has 669, and Comanche County has that. So if I were to take those two numbers, that's population for Comanche County. Tulsa County is this. Okay, so that's right at how much you can put into a single district. I don't think it would be possible to connect Tulsa County and Comanche County and be, on the lower side of that U-bound. So I think it is safe to make Comanche County a root of a district. It has to be separate from whatever Oklahoma County and Tulsa County are in. So that's node 8. So I can do the same thing. Node 8 should be, I'm going to say, is the root of the district. Okay. So you'll see here, I'm setting the lower bound of these variables equal to 1, which ultimately it's going to fix that variable to 1 because it's a binary variable. Okay, so I think I don't need to do this optimize. This is before I added contiguity constraints. But otherwise, let me rerun all of these cells, and let's just see if it takes less time than that 15 minutes from last time. Okay, so it seems like the bounds are converging more quickly than they were before. I think that makes a lot of sense. Okay, we've already found 39, which I think was optimal. Okay, yeah, this seems to be going much quicker. If you're working with a state like Alabama, for example, that has 7 districts, there's even more symmetry for that state because the number of kind of ways to represent a districting plan in this formulation is 7 factorial. So if you were to apply a similar sort of root fixing procedure for Alabama, that might also be helpful computationally. It might solve much more quickly than if you didn't apply such a fixing procedure. So it seems like it's okay. Yeah, it took about a minute. So much quicker than the 15 minutes from before. And I think that's not the same districting plan that we saw before. So this is an alternative optimal solution. So we have multiple optima apparently. Visually, it's reasonably pleasing. I don't know if this is a good districting plan to enact in practice, but guess that's true of any of the outputs of these math models. Okay. So now I'll conclude this video.